Hello friends, in this video I am going to discuss the various types of addressing modes used in MIPS architecture. The various ways of specifying operands in an instruction is known as addressing mode. There are 5 types of addressing modes in MIPS architecture. The first one is immediate addressing.
The format is like this, that is operation code, that will be 6 bits, then one register, it is called a source register. This is the temporary register, or result will also be stored here. Then this is the immediate value. Since this is immediate addressing modes, there should be an immediate data. Immediate data means the data will be provided along with the instruction. It will not be stored separately in the memory. Let us see the next addressing mode. So here, what is the difference? Here also you are having operation code. Actually, in all these addressing modes, the operation code will be only 6 bits. So you will have a maximum of 2 power 6 different instructions. So 2 power 6 means 64. 64 different instructions. For example, add means it is one instruction. Multiply is one instruction. But in the case of add, you can use any register. That will not be treated as a different instruction. So you will have 64 different instructions. But depending on the value you are giving, that instruction will be identified by the microprocessor architecture. The next one is register. In the case of register addressing mode, we have 3 registers. So you know that there are 32 registers provided in this architecture. To address how many bits you will need? 2 power 5. That means you need 5 bits. 2 power 5 is equal to 32, right? So there are only 32 registers. Those registers may be specified using 5 bits. That is why for each field they have provided 5 bits. Right, here also 5 bits. These are the register fields. This one is called as shift amount. This will not be used in add instruction or subtract instruction. This will be used only in shift left or shift right instructions. So for other instructions, this field should be 0. 0 means all the 5 bits should be 0. This field, function field, is 6 bits field. If these 6 bits are set to the value 32, 32 means you have to convert that into binary, and that binary value should be put here. For subtract, the value should be 34. If you want to do add operation, then this value should be 32. For subtraction, this should be 34. In addition to that, for add and subtract, the opcode is 000. That is, all the 6 bits should be 0. How do you know that, or how do you say that this is 00 and this is 32? See, when you are designing the architecture, you will fix this. If you are designing your own microprocessor and your own architecture, you can change this. For add, you can put 40. Any value you can put. But since we are discussing only the MIPS architecture, we have to follow the values given by them. Take an example. So without an example, we may not explain. Add $S1, $S2, $S3. In this case, how is it executed? S2 and S3 will be added and the result will be stored in S1. So S2 and S3 are source registers. The register number for S2 should be put here. Then for S3, the register number, that is 5-bit number, should be put here, and the destination register number should be put here. See, S1 means they will give some value, isn't it? That is, we have 5 bits to access 32 registers. Then this value will be 0, and this function value, since it is add instruction, the function value should be 32. Here also you should put 32. 32 means you should convert it into binary form. 6 bits will be taken, and that you have to put here, and here all the 5 bits should be 0. Here for $S1, there is a value, 5-bit value. That 5-bit value you have to give. So the same thing. So RS is nothing but S2, RT is S3. That is, we are mapping the instructions and the actual format stored in the processor. So actually in the instruction you see S3 is the last one, but here S3 is coming in the middle. Similarly, S2 is in the middle, but here it is coming to beginning of the instruction, right? Then S1 is here, that is the result. So how is it decided? Actually, this RS means the source register. Then RT is temporary register. You can use any temporary register. Even you can use $T0 here. Then instruction will be different. You have to put instead of S3, you have to use $T0. So depending on that, the value will also change. So this RT may be used as temporary register, or it can also be used as general purpose register, that is S register. But RD should always be used to store the result. Then shift amount, as I already told, it is 0. Function value should be 32. So this is called as register addressing mode, because in this instruction, S1, S2, all these registers are called as operands. All the operands are registers here. That is why it is called as register addressing mode. The next one is base addressing. It is also called as indirect addressing. It is also called as displacement addressing mode. So any name you can use. Whenever you want to explain the addressing modes, first you give the example. There is no other way. You have to remember some examples. Actually, I am giving only one example. That will be sufficient. At least you should remember this example. And based on that, you have to draw the diagram and explain. Right. Now, let us see this example. And let us justify how this is base addressing or displacement addressing or indirect addressing. So this is load word $S1, comma 32 within brackets S3. What this instruction will do? Actually, this 32 and this S3 will give an address. For example, 32 will be added with contents of S3, and that will be an address. This address will point a memory location. From that memory location, a word will be taken. Word means 4 bytes. Half word is 2 bytes. Byte means only 1 byte, 8 bits. So here the instruction is load word. So 4 bytes should be brought from the memory, and it should be loaded into the register S1. You know, all registers are 32-bit registers. So now how to draw a diagram for this? You know that this 32 is not data. It is a number directly given in the instruction. It is not a data. Actually, 32 is now address. So here, the format will be slightly different. You see, there is no field for the third register. We have only two registers and one address field. In the previous case, it was different. This is address, that is the value given directly in the instruction. So when you give the value directly in the instruction, it may be address or it may be a data. If you are using immediate addressing mode, then it will be data. If you are using this base addressing mode, then it will be giving the address. So this 32 will be stored in this field. Now you see the opcode will require 6 bits. Source register, which is source register here? S3 is the source register. $S3. What is this RT? RT is the temporary register, but it can also be used to store the result. So where do you store result? S1. So this in this field you should store the address of S1, not the data, address of S1. So when the processor executes this instruction, it will do this operation. So the complete thing, all the actually the complete instruction will require 32 bits, but the operation code requires only 6 bits. Add, subtract, like that. You should understand the difference. This is the operation code. This is the complete 32 bits is called as instruction code. You should understand the difference between these two. What is opcode and what is instruction code? Instruction code is bigger, 32 bits. It includes all the fields. Operation code means only this, the first 6 bits. Now we are taking this value 32 stored here, and we have to add that 32 with this S3. So I am putting S3 separately. Actually, the S3 is available here. You take the contents of S3, you add. This is the symbol used to add. So 32 and register S3 value are added, and that will give the address. So it will access the memory. Since the instruction is load word, you have to choose 4 bytes. You have to this instruction will read 4 bytes from the memory. If you use load half word, or if you use load byte, you can use the same instruction with LB. In that case, only one location will be accessed. That is called as load byte. Only one byte will be taken from the memory, and that will be stored in S1. So depending on load word or load byte or load half word, you will get the data, 1 byte data or 2 bytes data or 4 bytes word. Anything that will be taken from the memory and it will be stored in S1. S1 is here. How do you say that this is base addressing or indirect addressing or displacement addressing? Actually, this register S3 is called as base register. Even you can use S4, S5, anything you can use. But if you use the register like this, the content of this register will provide the address. So it is called as base address or base register. This 32 is the offset value. See, whatever content you are having in register, that will be added with the 32. So it is like a displacement, an offset, isn't it? So this 32 is the reason for giving the name displacement addressing mode. This register is the reason for giving the name base addressing. Also, here 32 plus $S3 is computed, and this is giving the address. So the address is indirectly given by this register. 32 is directly given in the instruction, but the register holds some value that is also combined with this 32. So this S3 is indirectly giving the address. Due to this S3 only, we are giving the name base addressing and indirect addressing. Due to this 32, we are calling it as displacement addressing. Next type of addressing mode is PC relative addressing mode. PC means program counter, which will hold the address of the current instruction being executed. See, if the instruction is available in the memory, we should give the address for that instruction. That is the current instruction being executed. Right? Only that instruction will be brought inside the processor and it will be executed. So without program counter, you may not access the current instruction. Now, if you want to go somewhere else in your program, this program counter value should be changed. Then only it will go to that address and it will access the instruction from there. You take this example, then only you will understand. This is branch on not equal. BNE means branch are not equal. S0, S1 registers, then 100. So what will it do? Here, S0 and S1 will be compared. If they are not equal, it will go to the address 100 and from there it will start to execute the instructions. Actually here 100 means it will not go exactly to the 100th location in the memory. You know that all instructions here are 4 byte instructions because this is the complete instruction, isn't it? So 4 byte instructions. So 100 means it is indicating the 100th instruction. To access the 100th instruction, you should multiply the 100 by 4. So it will go to that location. In addition to that, you are adding one more 4 because you should go to the next instruction. So when you are executing this instruction, if these two registers or contents of these two registers are not equal, then it will go to the address PC plus 4 plus 100 into 4. It will go to this address and start to execute. For example, like your if instruction in high level language. If both are not equal, even you can use branch equal. BE means branch equal. You can use the same thing. In that case, if these two registers are equal, then it will go to this location, PC plus 4 plus 100 into 4. So like that, you have many conditional instructions, but the basic concept is same, only this syntax. This is called as mnemonic. Mnemonic is the short form of symbolic representation of the instruction. It is a short form, or you can say that it is symbolic representation of the instruction. So it is branch on not equal, branch on equal. So this is providing conditional branching of execution. So how to draw the diagram for this? Anyway, branch not equal means there will be an opcode for that. That opcode should be put here, 6-bit opcode. Then here you have to decide which is source, which is destination. Where the result is stored, there is no result here. It is that it is going to the particular location and it is executing. No result is stored, but we need two registers. Those two registers should be compared. So the first register is stored in RS location and the second register is stored in RT location. And this value 100 is stored here. Now what will be the length? You see, this will be 6 bits for any register field, 5 bits, 5 bits. What are the remaining bits? 10 plus 16. So 16 bits will be available to represent this value. So that means you may use only up to 2 power 16 in this instruction. If you use 2 lakhs, 10 lakhs like that, you may not do here. So the maximum value that can be given in the instruction is only 2 power 16 because the number of bits used here is 16, right? And all these are combined, it will go to that address, specific address. So this is called as PC program counter relative addressing because the instruction execution is moved with respect to PC. If PC is 1000, then it will go to with respect to 1000, it will go to this location. If PC is 10,000, then with respect to this value, this will be added and it will go to that location. So relative to the PC value, the execution proceeds. So where that next execution should go, that depends on the current value of the PC. So that is why it is called as relative addressing mode. Next one is pseudo addressing mode. It is very simple. J 2500, jump 2500. Where you have to jump? In the previous case, it was conditional jump. But here, you are directly giving the address where the execution should go. That is given by the instruction directly. Jump 2500. What will happen here? This is the current instruction. The processor will jump to 2500 into 4. So you remember that in the instruction you are giving some value. Actually, it is not the address value. It is how many instructions you have to cross. That is why we are multiplying it by 4 because each instruction has 4 bytes. So if you execute this instruction, the processor will go to 2500 into 4, that is 10,000 address, and it will start its execution from there. 2500 is here, you multiply it by 4 and you add this value with current program counter value, right? And it will go to that particular address. So here also relative to the program counter value it jumps, but here the value is directly given. We are calling this as pseudo direct addressing mode. It is not exactly direct because it is also involving relative addressing. So pseudo direct addressing mode.